Welcome everybody to this online meetup. My name is Marco Palladino. Let me pull up the video. There we go. My name is Marco Palladino. I am the CTO and co-founder of Kong, and I am here today joined by Kevin Chan, who is a developer advocate at Kong. So today, we're going to be splitting this presentation into different stages. First, we're going to be setting up a little bit of context to what service mesh is, what Kuma is. And then on the second part, Kevin will pull up the terminal and go a little bit more hands-on. So we're going to be seeing Kuma running in production. We're going to be using Kuma to configure the networking for a sample application that we've created. And of course, we're going to be answering questions. So I would like this to be interactive. I believe that Zoom has a chat function as well. So if you want to ask questions there, they'll be great. We're going to be having some Q&A at the end of this meetup. So just to confirm, Kevin, you can see my main slides, correct?
Yep, I can see them.
Okay, perfect. So in order to understand why service mesh is important and why Kong decided to build Kuma, we really have to understand the changes that have been happening in our industry. A few years ago, our industry made some important transformative shifts. They were kickstarted by Docker in 2013 and by Kubernetes in 2014. As you know, we've been moving away from large monolithic applications to more microservice-oriented applications. Microservices were not invented in 2013 or 2014, but Docker and Kubernetes really made it easy for any developer out there, any organization, to make this change into containers and to have a platform and a self-service ecosystem so that we can easily deploy these containers on top of our infrastructure. Well, so obviously, this is a shift that revolutionized not just how we build software, but also how we drive new business. And it's led by important technologies, by patterns, and by vendors. For example, the clear winners are the cloud, container, orchestration platforms like Kubernetes and so on. It is very important to understand why this is happening. And really, like with any other technology transformation, this transformation happened because these new technology patterns have been emerging as clear winners in the future of technology. The importance of running distributed, highly available software and decoupled software was one of those goals that led this shift. Why? Because distributed, decoupled, it's good for business. We want to be able to grow our business. We want to be able to get more users. We want to make existing users happy. And to do that, we must build reliable applications. We must be deploying very often to fix bugs. We must have an infrastructure in place that allows us to iterate on top of our products. When applications grow, as we know, if they grow in a monolithic way, then it becomes harder and harder for us to be able to get that velocity and to be able to get that reliability. And so as part of this shift, we decided to distribute our software, make it more highly available, running it in the cloud, because we do not want to manage our own cloud, as well as deciding to expose some of the services that are part of our applications as individual independent services that different teams can iterate independently. And in this new era of software, it's a new era because it's fundamentally different from the monolithic era. We celebrate the importance of service connectivity as the underlying enabler to this new paradigm. In a distributed and decoupled world, our distributed and decoupled services that run on a network. And to connect them together and to enable that service-to-service traffic, they use an API. APIs really are the backbone of this new way of building software. They've always been. APIs over a network, they were very important in the monolithic days when we wanted to enable external developers and external consumers or partners to consume our monolithic application. Or if we built a mobile app, we had to run it in an API. But of course, the more distributed and decoupled the software become, the more APIs we're going to be having and the more network traffic we're going to be having. When we talk about services and APIs, we really mean every kind of service and API that runs on our system. It's not just traditional HTTP service that are being consumed externally by other services, but also databases, login collector, caching systems, all the microservices that make our applications usable to the end user. And the most radical underlying shift from monolithic applications to microservices was replacing the CPU with the network. We don't make function calls in a large monolith anymore, where everything is being deployed as a single binary, as one component, but we make API calls on the network to consume all the services that we need and that have been decoupled over time. As part of this transformative shift, the network is taking a bigger role within our applications. But of course, we always had network traffic even before. So when you think of a monolith consuming a database, that request, of course, was going over the network. But what has changed now between back in the days and microservices is the number of services that we have that overall define a bigger number of network requests. We have the scale, it's much bigger. And that wouldn't be a problem per se, except that back in the days in a monolithic world, those function calls were happening on the CPU. And the CPU, as we know, is reliable. The monolith was hard to scale, hard to build, hard to deploy, but at least the CPU calls were working. If we called a function being defined in an object, we could have been reasonably expecting that function to be invoked or to be executed. And of course, the monolith didn't scale well, and we had to replace it over time. We had to decouple it. But by doing so, we've replaced the reliability of the CPU with the unreliability of the network. Because now lots of these function calls are happening as in the form of API requests over the network. And the network is problematic because it does introduce a series of problems that we didn't have before. Problems like, for example, encryption, identity. We want to be able, the network, as we all know, is by default insecure. And so how do we secure it? How do we protect it? How do we encrypt all the traffic that goes from one service to another? And as we do that, how do we assign an identity to every service so that if we want to change the configuration of a specific service, we can do that by identifying that service and that service only in our policy configurations? How do we determine if a service should be consuming another service or maybe not? How do we determine, how do we route the requests? Once we are running over a network, and once we have network APIs of any kind, not just HTTP or gRPC, but even like a Mongo database, for example, or Postgres database, how do we determine if the request should go to that replica, to that service, or to that version of the service? Therefore, how do we implement deployments? How do we implement the versioning? How do we implement blue-green and canary releases, patterns, and so on and so forth? As well as the network requests, of course, they can always fail. The network is unreliable, can be slow, the latency can be high, our request may or may not time out. So how do we find out if something is wrong, where exactly it went wrong? We need to have logs, we need to have metrics, we need to have observability in place so that we exactly know where things go wrong and when they go wrong. And most importantly, as we transition to microservices, we want different teams to be able to create different services and expose them to other services and maybe even other teams or other products. But these teams are now going to be working together into deploying these services in an environment where we don't want one team to be able to impact negatively another team. So how do we create a zero trust environment for all the teams to be able to work together without stepping on each other's foot? And also, of course, to enforce some level of security so that one team cannot, for example, change the deployment or routing settings of another service that has been built by another team. So these are all things that back in the days in the monolith, we didn't really have to worry about. But we decoupled the monolith because we wanted our applications to be more reliable, more distributed, and we are fixing some problems, but of course, we're introducing some other problems, like the ones we're seeing here. And even back then, in reality, if you think about it, even back then, in the monolithic world, we would take care of those network requests. So first of all, a network request would always happen, even back then. Even if the monolith was talking to a database, that's still a network request. We would write maybe code that would take care of that request and maybe recover a faulty request. It would log that request. It would try to deal with the networking connectivity of that request. But we also know that most of the times, perhaps that wasn't happening. So developers, how many developers or how many applications do we know that are going to be failing with no recovery attempt or with no meaningful logs when, for example, the database fails? We all know that that happens all the time. And of course, if we only have one monolith making requests to the outer world, well, maybe we can build this into that specific monolith and we can add this logic, extra logic that's separate from the business logic we want to implement for the actual product we're shipping. But we want to build it and we can perhaps build it if the monolith is only one monolith or it's only one component. But we all know that's not the case. Let's assume that we're not, let's assume that we're going to be building this network management. We're going to be writing more code to handle that network. And in a large organization, some problem starts to happen. The application teams will build something for their app, and then maybe another team will build the same network management in their own monolith or their own application, and so on and so forth. And what we end up with, it's a very fragmented situation. Every team is going to be re-implementing the same things in different ways. That creates consistency problems. It creates perhaps even a compliance problem. Maybe one team is implementing mutual TLS in one way, another team is implementing it in another way. And effectively, we end up with a fragmentation problem that creates a big mess here, because now we are letting the teams taking care of that network management. And once they do it, their job is not building network management. Their job is shipping a product. And so they're going to build their product, then build some network management here and there, push it in production. Over time, we're going to be ending up with a big fragmentation. We fragment how we observe and log this traffic. We fragment how we implement routing strategies when it comes to moving traffic from healthy services to unhealthy services. We fragment the architecture of the entire organization by letting the teams whose job is not managing the network doing something they shouldn't be doing. And this can cause a big damage in the long run for the entire org, and it really stimulates the creation of something we don't want to see happening, and that's shadow IT. So we want to fix this problem. Now, as we discussed before, over time, we're going to be decoupling and distribute our software more and more. And this problem, all of a sudden, becomes so large with so many services that can really harm the velocity and the speed. It can increase the technical depth of the entire org. And we need to do something about it. At the same time, we cannot ignore the problem. I guarantee you that every organization in the world has built applications that reinvent network management. So maybe instead of building this logic within our monoliths, and by the way, if we do use different programming languages, then we're going to be building the same thing over and over again in different languages, which makes it even worse. So let's say we don't want to do any of this. Let's say that maybe we can build all of this functionality in such a way that regardless of what programming language or framework our developers are going to use, we can provide those network functions, connectivity functions to all of them by shipping these features in a separate binary. So we build all of these once, and it's a separate binary. Now, when we do that, for this binary to work, this binary would have to be on the execution path of every request that the services are making when they're consuming another service, or when they are requesting or accepting a request from another service. If the binary that we're building that's taking care of the network is on the execution path of our requests, now we can do things like enforcing security, enforcing mutual TLS, TLS termination, logging, observability, and so on and so forth in one place without having to have that code built into the service. Now, this has two advantages. On one end, the application teams that are building the service don't have to worry about this. So they are faster when it comes to building what they should be building, which is the products they should be shipping. And on the other end, we have some consistency on how these functionalities of the network are being implemented, because they're in one place, in one binary. So if we want to make them, if we want to change them, or we want to create a new feature, we update the binary, we reship everything again, and the binary takes it from there. This really becomes worth it if the binary does not add too much latency. Of course, now that we have this binary on the execution path of every request next to each service, we want this binary becomes an extra hop in the network. So we want this extra hop in the network to have as the smallest latency as possible so that we can make this new pattern viable. So what if we deploy the binary on every replica of every service on the same host, on the same virtual machine, or on the same pod if we're using Kubernetes? Now, if we do that, the latency between the binary and our service, it's minimal, it's very small, because it's on the same machine. It's never going to go outside of that machine. So we're going to be having a little bit more latency, but if the latency is small enough and the benefits that we get from that binary are big enough, then that's a cost perhaps we're willing to pay. So this is very good only if the binary does not add much latency. Now, when we build services and we want to deploy them, and we want a service to be able to consume another service by making a request over the network, we don't really care if we're running all of this on virtual machines or Kubernetes or bare metal. This is a problem the problem itself, it's platform agnostic. It doesn't really matter where our workloads are running, where the services are running, because as soon as they make a network request, we have to take care of that network request. Therefore, this binary, the more portable it is, the better. Because then if we have services running on virtual machines, or maybe we have a team that's running on virtual machines, we can ship this binary to them. But then if there is another team running on containers, and this can be containerized, we can also ship that to that team. Effectively, this pattern is platform agnostic. The more portable it is, the better, because then we can take care of all the use cases we have within our organization. Now, with a proxy binary alongside our services, we can now add as many of them as we want. And if we build them ourselves, because remember, one of these services might be a database that we're not building ourselves. We just download it and run it. But maybe other services are services that we are building, like APIs that we're building or gRPC services we're building. Now, because we have a binary, we can use any framework or any programming language or any service out there. And because the proxy binary is portable and it's a separate process, we can effectively support any programming language and any framework. It doesn't have to be built inside of the service. It's a separate process. Therefore, we can use this binary across pretty much everything we're running. And that's pretty good. Now, what this achieves is consistency. If we want to implement mutual TLS, if we want to implement routing, if we want to implement observability, all of these different services across any language, any framework are now going to be standardized when they do that. This, in a way, also speeds up application development, since the teams don't have to worry about dealing with the network anymore. The same way, we don't want to be dealing with managing a data center. Therefore, we go to a cloud vendor, Amazon, Azure, GCP. For the same reason, we don't want the teams to be dealing with their own network management. this proxy binary will do it for them. And of course, like I said, we always had network traffic even before. So think of a monolith consuming a database. That request, of course, was going over the network. And obviously, this proxy and the functionalities it provides are useful for any service that makes any sort of request to the network. It can be a monolith, it can be a microservice application, it can be a virtual machine, it can run in a container. It doesn't matter what it is and where it runs. As long as we have incoming or outgoing network requests, this proxy can help us. Why do I call it proxy? It's a proxy because when the request goes outside, so when a service wants to make a request to another service, it does that request, and transparently, this proxy will take over the request and then take it from there. Because the contact points between one service and another is this proxy binary, then the proxy binary can implement TLS termination and all sorts of things without the applications having to know or worry about it. But this proxy, in a way, it's also a reverse proxy, because when a request comes in, the proxy will receive this request and then forward this request, reverse proxy it to the local service, right? So this proxy binary can be both a proxy and a reverse proxy, depending if the request is outgoing or incoming. And because, like we said, this is only worth it when the latency between the proxy binary and the service binary is minimal, we would also want to run the proxy as close as possible to our services. So in the case of a virtual machine, we would want the proxy to run alongside our service process. So let's assume that we have a virtual machine and the service, it's a Java application. We start the virtual machine, we start our Java app, and then on the same virtual machine, we also start another process, and that's the proxy process. So they're running together on the same underlying virtual machine. Likewise, on the same pod, if we're running on Kubernetes, we can make that proxy a sidecar proxy. We can make that proxy a sidecar container, which is a fancy way of telling Kubernetes, when you're scheduling that container, always make sure that because this container is a sidecar container of, alongside these other containers, basically every time we schedule them, we have to schedule them all together on the same underlying host. This is what we want to get in order to make sure the latency is always minimal. Like I said, if the latency is too high, then this is not going to be feasible. So we have to reduce that latency. Now, this also means that because we're going to be having one of these proxies running for each replica of our services, we're going to be having many, many proxies running around. This requires the proxy to be lightweight. If it wasn't lightweight, then the proxy would, because we're going to be having many of these, it would probably consume too many resources and make this pattern unfeasible. Every instance of every service is going to be having this proxy binary deployed. That means, for example, if we have two different services, and each one of these services has, let's say, 5 instances, so 10 total, we're going to be having also 10 total proxies running around, one for each replica of each service. Since the proxy will be dealing with the inbound and outbound service connectivity, obviously there must be a way for us to configure this behavior. What if we want to change the routing setting? What if we want to send the observability logs somewhere else? What if we want to change any configuration about this proxy? So the simplest way would be to start the proxy with a configuration file that determines what the network policies are. Like mutual TLS should behave this way, the routing should behave this other way, the logging should behave this way. And so we have this file, we start the proxy, we deploy the file, and that's how we configure the system. But this can be very problematic because if we ever decide to change the configuration, now we need to restart these proxies with a new configuration, and we must propagate this configuration all the time. So there must be a better way to do this. Remember, we're going to be having many, many proxies running around. So the way we configure them must be better, because otherwise it's going to be a mess. Every time, we don't want to be restarting these proxies every time we want to change the configuration. So what if, instead of doing this, we pushed our configuration in one place, a place that's going to be external to all the services and all the proxies. And we found a way to propagate this configuration to the proxies in a dynamic way. So we get rid of these configuration files, we put all the configuration somewhere else, and this somewhere else, this hypothetical place, would be effectively the source of truth for all the configurations, for all the proxies, for all the services we're running. Every update we want to make to the configuration will be made in this source of truth, and then this thing will propagate the configuration to the proxies. This source of truth would not be on the execution path of our request, because the only job it really does is collecting the configuration and propagating it. But when we make a request from one service to another service, we're not going to be going through this system, right? This system would connect only to the proxies, but not in between the requests that our services are making. So in my example here, I call it the conf service. Now, since the proxy will be dealing with the inbound connectivity and outbound connectivity, and it needs a configuration for that, that configuration, like we said, could be dynamically propagated by this central place. This control plane, we can call it control plane because it controls the configuration, is going to be separate than the data plane, which identifies the proxies. The proxies are on the data path of the requests, service-to-service requests that we're making. Therefore, they are on the data plane, whereas this central place that stores all the configuration would be in the control plane, because it controls the proxies and controls their configuration. These are terminologies that have been borrowed by the networking industry. Back in the days when we were running our own data centers and we were having racks with a bunch of servers and, let's say, switches and routers and so on, we had the same problem. Every time we wanted to make a change in a switch or in a router, we didn't want to go and open the rack and make that configuration and then restart the router. We wanted to have a central place to push all this configuration through. So the switches and the routers in a more traditional networking landscape, those would be the switches, the routers, the actual hardware that would be on the data path of every networking request. And this other thing that would collect the configuration and then push it to the routers and the switches, that thing will be the control plane. So these are very popular in traditional networking terminology that we can apply in our example here in its software version. So instead of controlling hardware, we control software. And the software that we control are the proxy binaries on the data plane. And just like that, we have determined and identified what service mesh is. Service mesh is a pattern that wants to make connectivity among our services more reliable, more observable, more secure. And to do that, we introduce two components. We introduce a proxy that's on the data path of our requests, and then we introduce a control plane, which is a component that we're going to be using to push the configuration to our proxies. If we do this, then we can control the network of the entire application and all the services that are part of our application from one place. The alternative is to build all of this within our services. And like we've explored, if we do that, it becomes a big mess because the teams are going to be doing it in a different way every time. They have to maintain it, they have to build it. And if we support multiple languages, then we have to rebuild it in different languages. This is what Service Mesh is about. Service Mesh can run as a pattern, can run across any technology, any platform. It's not tied to virtual machines or Kubernetes. It can run pretty much everywhere. There are different implementations that we're going to be exploring, and of course, one of them is Kuma. So if we zoom out, we can see how it looks like with many services. So the control plane will connect to the proxies to push that configuration, keep them always up to date. But then effectively, the proxies are on the execution path of all the requests. So service mesh is not a new thing. It's a better way of doing something that we've always been doing one way or another. And I know that we hear a lot about service mesh in the context of microservices and containers, but really, like I said, any architecture can benefit from this, including monolithic applications. Basically, we can use it whenever we have a network connectivity between two or more services. This pattern can also be applied for obviously both east-west traffic within a data center or a business boundary. A business boundary can be, for example, a product or a team or a line of business, as well as we're going to be applying these proxies also for north-south traffic in order to protect and secure traffic among different business boundaries, among different data centers or different regions. The control plane will connect both. Now, there are different implementations that you can use, right? So today, we're going to be exploring Kuma. Kuma takes a different take when it comes to service mesh. Kuma allows you to implement this pattern without you having to worry about it. So the proxy binary and the control plane already comes with Kuma. So if you want to make your connections more reliable, you download Kuma and that's pretty much it. Kuma is technically a control plane. So Kuma allows you to collect this configuration and then push it to the data plane. And the data plane that Kuma supports is Envoy. Envoy and Kuma are both open source. So you can go on the GitHub repository, you can download Kuma. And when you download Kuma, Kuma already takes care of the complexity of running and configuring Envoy. Many service meshes out there, they require you to be a little bit more hands-on with Envoy. Envoy is a very popular proxy when it comes to service mesh implementations. But it can get a little bit complex sometimes. And if we are trying to deploy this to as many teams as possible, we want to be abstracting away that complexity. So Kuma does that for you. Kuma abstracts away Envoy, so you don't even need to know that you're running Envoy. But if you are a power user and you want to go deeper into the configuration, then Kuma, of course, allows you to be able to do that. But you don't have to do that by default. And Kevin will demonstrate that in a few minutes. So what Kuma really does, it provides you with out-of-the-box policies, like mutual TLS, like routing, like logging, tracing, and so on, that you can apply since day one on top of any network requests among any service that listens on a network. So it can be a database, it can be a microservice, it doesn't matter. What Kuma does, Kuma connects to Envoy by leveraging the XDS API of Envoy. So Envoy, it's a very good technology because, and the reason why Kuma and in general, you're seeing Envoy around quite often in service mesh implementations, it's because Envoy provides an API that allows you to dynamically configure the proxy via a gRPC streaming request. So what Kuma does, it enables these gRPC streaming requests between Kuma itself and Envoy. And every time we make a change into Kuma, then Kuma will take it from there and propagate it to the right Envoy data planes. So we're going to have all of our network traffic on one side, microservices, databases, events, caching systems, can be ingress, can be egress. Kuma integrates with Kong gateway if you have an API management use case. And on top of all this traffic, Kuma makes that traffic more secure, more reliable, more compliant, more observable. It allows you to implement routing strategies, versioning strategies. And it allows you to do that in a platform agnostic way. And this is really where Kuma is different from other service meshes control planes out there. Kuma has been built with portability in mind. When we look at all the environments that our organization is going to be running, we're going to be seeing adoption of Kubernetes from some teams, from some line of business, but then we're going to be seeing also lots of virtual machine workloads. arguably, it's going to take a while for most of these workloads to be transitioned to containers and Kubernetes. And some of them, they will never be converted because it makes no business sense. So Kuma, we did a good work with Kuma when it comes to abstracting away the underlying platform, which means that if you're running on Kubernetes, you can configure Kuma in a Kubernetes native way with CRDs. But if you are not running on Kubernetes, then Kuma provides you with a RESTful API or a CLI tool that you can use to configure the system and the policies and the network with no Kubernetes knowledge whatsoever. Effectively, this makes Kuma deployable across the entire organization, not just Kubernetes-specific environments. Why is that important? Because the bigger the mesh, the more value we get from it. The alternative is making the teams build that by themselves, which again creates fragmentation. Now, Kuma also ships, by the way, with a GUI out of the box that's getting better and better. So we're making our hyper-focus and hands-on and making sure that we are receptive to the community, we're receptive to your requests, and that there is also a Slack channel that you can use to chat with us. Another thing that Kuma does that's a little bit different, it's multi-tenancy. So if you wanted to support different teams or different products or different lines of business, we, pragmatically, these different teams are going to be using mesh at different times. So with other service meshes, you would have to deploy a control plane, an instance, a cluster of your control plane for each team, for each time you want to create a mesh. With Kuma, we support multi-tenancy since day one. You deploy Kuma only once to support the entire org. You don't replicate Kuma for every single mesh you're trying to create. That's important because if we are planning to support the entire org, we can substantially lower the operational cost of running Kuma by leveraging this multi-tenancy feature. Being simple to use, being portable, being multi-tenants with a low operational cost, as well as obviously feature-rich, these are goals that Kuma implements. So let me give you an example. So Kevin is going to be running this, but for example, let's say we want to enable mutual TLS. Well, to enable mutual TLS with Kuma, we can do that in two different ways, depending if we're running on Kubernetes or on virtual machines. But basically, if we run on Kubernetes, we create that CRD, we create that policy, we apply it, mutual TLS enabled true, and boom, now we have mutual TLS enabled across all the traffic, across every data plane. If you want to do that with VMs, we can then use the CLI or the API to do the same thing. Let's say that we want to look at a more complex routing example, and Kevin is going to be demoing this live in a minute or two. Let's say that we want to capture all the traffic that comes from our backend service going to Redis, and we want to split this traffic so that 9 times out of 10 goes to version 1 of Redis and 1 out of 10 goes to version 2.0 of Redis. We can do that with a simple configuration that we can push either in Kubernetes or in virtual machines via a YAML configuration. Either one, Kuma will reconcile this configuration within the control plane. So you can use both, it doesn't really matter. Kuma has that abstraction layer like I mentioned. Obviously, there is more policies you can apply. Today with Kevin, we're going to be looking at some of them. But pretty much the security policies, the routing policies, the observability policies, all of that is being taken care of, as well as an integration with Kong Gateway, so that you can create a network overlay among all the services you're running. And that network overlay is being provided by Kuma. And then for the services that you want to expose to an external consumer, an external team, or an external partner, you want to govern the traffic as a product almost. And so you would be using an API gateway to do that. And so with the Kong, Gateway, and Kuma, you effectively have the full life cycle. So you have your connectivity taken care of by Kuma, and then you have the gateway being allowing you to offer some of those services as products via through the API gateway, right? So they integrate very well with each other, and they fit different use cases. Kuma, it's more of a networking connectivity use case, as opposed to Kong, which is a full cycle API management use case. Like I said, Kuma is open source. You can download Kuma for free. You can go on kuma.io/install. You can check it out. But now, let's not waste any more time. Let's jump straight into the demo. So I'm going to be letting Kevin share his own screen so that we can look at a few different use cases with Kuma in action. So Kevin, are you there?
Yep, I'm ready to take over. Let's see. All right, there we go. Can you see my screen, Marco?
Yeah, I can see your screen.
Awesome, and thank you for the great introduction to Kuma. So, hey folks, my name is Kevin. I'm the developer advocate at Kong. You might have seen me on either like Twitter or the Kuma Slack channel. So always feel free to reach out if you have any questions. Today, I'm going to be giving an overview, a quick demo of how Kuma works in production. So to illustrate that, we built a sample application that we thought might best illustrate all the capabilities that Kuma has to offer and that you can use in your organization. So to find that, you can, if you check out the Kuma repository, our main repository, and you go down to the examples directory over here, it basically points you to our Kuma demo application. Here we can see a really good overview in a diagram of how our application is built. It's a very simple marketplace application. Think of like Amazon, where you can shop for items. We have a front-end app, which is a GUI, a backend API, and two databases. So Marco talked earlier about having decoupled services. Here we see we have 4 individual services. And he also mentioned that some services are services that you might not build, such as the database we're using. So both Redis and Elasticsearch are things that we didn't build. We just pulled the Docker image and we kind of loaded it up with items. And Kuma still is able to support those services. Kuma's, you can deploy it in 2 different modes, Kubernetes and Universal. So you can follow the links here, and it'll point you to respective readmes that can kind of guide you through how to deploy it. I'm going to go through Kubernetes mode today, so I'm going to go through here. Awesome. So it points you to the Kuma demo repository, so it's slightly different as you see up here. This is where we host all the code for the Kuma sample application. And within that, we have different kind of guides for you based on how you want to deploy it. So I'm going to skip the setup because I have everything set up already. But you can easily walk through this yourself. And I'm going to go straight to all the policies that we have enabled down here. So before I jump into enabling the policy, this is what our sample application looks like once you deploy it. You can have, look at clothing items. You can read the reviews. All the items that you see on here are stored in Elasticsearch, and the reviews for each item are stored within Redis. So let's dive right into how can we secure this application? We already have all the services up and running, but traffic between the services are not encrypted, and this is where mutual TLS comes in handy. The mutual TLS policy enables you to automatically encrypt all MTLS traffic for all the services within your mesh. By default, mutual TLS is not enabled in Kuma, but you can enable it very quickly just by using the configuration Marco mentioned earlier, where you do enable true. So we go ahead and apply this policy to our mesh. If I go back to my terminal here, I'm using kubectl apply, and on the mesh resource, I'm saying I want the mutual TLS to be enabled here. So you'll see enable true on the last line. I go ahead and apply this. You'll see the mesh resource is now configured. If I go back to my application and refresh it, the application no longer works. Because with mutual TLS enabled, now we need traffic permissions to basically give permission to each service and tell which service it can communicate to. So without, just as easily we can enable mutual TLS, we can also enable the traffic permissions with kubectl apply. So here for the traffic permission, we're going to use the traffic permission CRD. So in Kuma, all the kind of policies are CRD based, so you don't have to do anything outside. You can kind of stick to the Kubernetes conventions and not have to use Kuma CTL in this instance. But here we're just going to do a traffic permission where we enable sources, all sources, to talk to all destinations. This basically gives the capability for all services to talk to each other. Let's quickly apply this to our mesh. You'll see that traffic permission named everything is created. And now if we go back to the application, you'll see that the application looks like how it worked before. But now the kind of underlying like communication is all encrypted, which is good for our security. So before I go further into any other policies that we have, let's go look at what our GUI has to say. So Marco mentioned earlier, Kuma ships with the GUI. It's by default, if you port forward our control plane pod on port 5683, that's where you'll see the GUI. So if you go back to our terminal, you'll see on the left here, I'm actually port forwarding the control plane pod with the port over there. This is why we can access it in Kubernetes. And here we have our data planes. So we inspect our data planes. We'll see all the respective the services that we have. Basically, each service will have a data plane running next to it. So we have Elasticsearch, our demo app, our backend, and our Redis service. And if we go into our traffic permission, which is something we just created to enable services to communicate each other with mutual TLS enabled, we'll see that everything Kuma demo traffic permission is there, and you can kind of view it and see what the entity has. So this gives you a very easy place to visualize what's going on within your mesh. And while you cannot add configurations through here yet, it helps you kind of understand what's happening in your mesh in a GUI format. Okay, so now let's continue and see what other policies we have. So now that we talked about enabling traffic permission for all services, there are instances where, let's skip down for here first. There are instances where we don't want all services to talk to each other. That kind of a broad like stroke of traffic permissions might not be something you want. So in that instance, let's say we want to disable our Redis service. Maybe someone is spamming it with false reviews to kind of hurt the integrity of our our marketplace. We can easily do that with traffic permissions too. So I'm going to go ahead and delete our existing traffic permissions, which gives all services ability to talk to each other, and add two very specific traffic permissions here. The first one you see up top is basically saying I want to allow all the front-end service to talk to the back-end service. So using the kind of same source and destination service matching here, I can specify very specific sources and destinations I want to allow communication.
And this, Kevin, as we all know, it's very important so that we can segment the traffic and, for example, prevent certain services from consuming other services that they should not be consuming. So let's say that in a bank, we do have a specific service that gives access to the customer information. Well, that's very sensitive. And so we want to be able to limit what's the scope and what other services can get access to this. Only the allowed ones should be able to do it. Now, in a traditional use case, we would implement something like this by either blocking the firewall or changing how that billing service is being protected via security group in the cloud. But it's not portable. Each cloud has its own way to do that unless we deploy or build this within a specific application. So with Kuma, effectively, we can do this across any platform. We can implement ACL rules on what's allowed to consume what, segment that traffic in basically a few lines of code.
Exactly. And so let's go ahead and just see what this few line of code can do for us if we apply that to our mesh. So you see we created two traffic permissions here, and that should be reflected in our GUI. So we can see that it has taken our control plane has registered that. And our application looks like nothing has changed. And that's because our Redis service only handles all the reviews. So the front end, the GUI can still talk to the backend service and fetch all the items from Elasticsearch. But now if I look at, let's say, the readmes for my hot floral pants, the service no longer works, and the reviews are no longer populated because the backend service cannot communicate to Redis and cannot fetch those reviews that we want to see. So just like that, with a few lines of code, you can enable, you can kind of be very specific and very granular of how you want your application to communicate with one another, the services within your application to talk to one another. So before we kind of continue with our demo, let's quickly enable our Redis service again. And that just goes back to adding another traffic permission that gives permission for the backend service to communicate with the Redis service. There we go. And once we apply that, you'll see that it takes effect immediately. And our Redis review is now working again. Awesome. So now we explored mutual TLS and how traffic permissions enable you to have services communicate with each other and with mutual TLS enabled. Let's look at traffic routing. It's kind of one of my kind of favorite features with Kuma. So before we look at traffic routing, we're going to go ahead and scale up different versions of our backend. So when we deployed Kuma sample application on Kubernetes, we actually have a V1 and V2 version of the backend. The V1 version, if we look at our application now, had the V0 version, which is the current version, has no sales. So we have no capability to we have President's Day coming up. A lot of vendors are doing sales. Our application cannot support sales at this point. So we want to test out a new version of our application that can handle sales for our items. So by doing so, we built a V1 version. So we're going to scale that up. And we built a V2 version, which gives 2 sales. And you can see that visually in a second once we scale that up. I'm going to check the pods real quick. Second, check pods in Kuma demo repository. You'll see that our V1 and V2 are up and running now. We can also check if the data planes are up and running by looking at our GUI, and you'll see that now we actually have 2 more data planes that last connected less than a half minute ago, and they both have the tag of version V1 and version V0. Our existing one has a version V0, and this is V2. So now we have 3 data planes for specific backend applications, and they're tagged separately. And we can utilize those tags to do traffic routing, so we can do a canary deployment of our new versions in a safe manner. So this is kind of how it looks right now, right? The front end talks to 3 different backend services, and we want to specify which services it can talk to before to roll the new features out safely. Before we add traffic routing, it just kind of load balances to all 3 evenly. So you'll see this is what happens when we have 1 sale on our page. If I kind of refresh it, this is what happens to 2 sales, right? So roughly 1 out of every 3 requests goes to each individual service. And we don't want that. We want to be more specific with how our traffic is routed to the new versions. So that's where traffic routing comes in. So traffic routing is another policy we have here. So if you look at the kind, we have traffic route. And what traffic route enables you to do is, give a kind of specify how much, like what percentage of your traffic you want to go to each service. And Marco demoed that earlier on his slides, and we're going to show that in practice. So here we have, we specify that the same idea of traffic permission, we're routing from our front-end service to our back-end service, but we want to specify exactly which versions of the back-end service we're routing to. So we're going to give a positive weight of 80 to our back-end service of V0. So this is our existing application. We know it works well. We know it doesn't break. So we want to, send majority of the traffic there first before we roll out the new features. Next, we're going to send a positive weight, roughly 20% of our traffic to our backend service of version V1, which enables 1 sale. And we're going to give a weight of 0, which is basically, we don't want to send traffic to the V2 version because we're not sure how 1 sale would do for perhaps our numbers, our quarterly numbers. So this gives us a very kind of safe manner to deploy our new version of our backend if we're going to have it kind of the capabilities of handling sales before President's Day. So we go ahead and enable that. Traffic route is now created. And if we go back to our marketplace now, you'll see that V2, which is the one with 2 sales, will never appear. And V1 will seldomly appear because only 20% of the traffic is routed to it. So as I refresh each time, you see we're still getting kind of the original version. And I think it was roughly 7 refreshes before I got this sale. So the traffic routing is working as expected. And we can always check those policies are in effect by checking our GUI here. So you can see that we have that front end to back end traffic route with the weight configuration that we specified earlier. So lastly, what we're going to demo here today is the logging. So I skipped over it earlier because I wanted to kind of give time for the logging container to be deployed. But what we're doing is we're sending logs to a hosted log stats service. And to do that, I had to deploy a kind of a forwarder over here that's in this YAML file. With that deployed, so let me check real quick. So we have kubectl get pods in the logging namespace. What we can do is, perfect, we have it up and running here, is we can push logs from our mesh to any Logstash service that you might have. So to do that, first you have to go back to the mesh resource. Earlier, we enabled mutual TLS on our mesh. Next, we're going to enable logging on our mesh. And here you can see we just add this additional section here that says logging. And what we're going to do is first specify, what kind of data we want to send to, we want to log. We're going to log stuff like, the destinations, the upstream host, the source, the amount of bytes we received, the amount of bytes that are sent between the services. After we enable that on our mesh, we also have to create another kind of traffic log resource, a policy that basically says, great, these are the kind of things you want to log, but what services, what kind of traffic do you want to log? So we're going to specify that we want to log basically all traffic between all services here.
And with that, and sorry, Kevin, by doing this, by the way, this is not just HTTP traffic or L7 traffic. This is any L4 traffic within the entire architecture. So by enabling this, we can log pretty much anything that's being sent or received within our systems.
Yeah, and that's something you just specify up here in the format. This is just a few of the data points that you can log right now that we use to illustrate what you can do. So I'm going to go ahead and apply these two. First, updating the mesh policy and adding the traffic log policy. So we can see the mesh is configured and traffic log has been created. Here, we're going to, kind of just generate some traffic to our sample application. So, we have something to log. And as we generate this traffic, what's being happened is it's being forwarded from the Logstash container that you saw earlier that I deployed to this logly instance I have here. And if we refresh it a few times, you'll see that the logs are coming in now. Where we have, I think it's easier to view like this by grid view. Actually, let's do event view. Sorry. So you'll see that we have events such as from our backend destination to our front end host source. So the front end source is to the front end service. So here we have the byte sent, byte received, which are all things that we specified earlier in the mesh resource, where we're, sorry, this one right here, where we're saying, exactly what we want to log. And that's kind of all the policies I wanted to demo. Is there anything else, Marco, you would like me to cover?
No, thank you so much, Kevin. I think this is good. Obviously, there is a 10 plus policies available out of the box for Kuma. So among them, there is also Prometheus integration with Grafana. There is a default Grafana dashboard you can also use, health checking, and so on. So we are building more and more of those policies as we speak. And the whole point is that we want this to be simple to use. So the GUI is going to get better and simpler. The way you apply this configuration is going to get even more simple. If it's simple, simplicity is a feature. And so if it's simple, then that really differentiates Kuma from some other control planes that are quite complex to run, quite complex to deploy. So, so Kevin, if you stop sharing your screen, I'm gonna wrap up real quick. All right, so I'm sharing mine. Can you see it?
Yep.
Perfect. So let's recap a little bit. We have discussed how we want to build more reliable applications. And as we transition them to cloud native applications, as we make them distributed, as we make them decoupled, as we start using microservices, we're going to be having more and more network requests that we have to be taken care of. Of course, those requests, we still have them in the monolith. If anything, the monolith talks to a database, that's a network request, right? But that network request becomes more and more unmanageable the more of them we have. And so we talk about introducing service mesh, which means taking away of the network management from our services, from our apps, and pushing it into a separate binary, a proxy binary that we can deploy alongside every service and that we're running. Now, the proxy binary will take care of that network request, of that connectivity. We don't have to worry about it. But of course, the more proxies we have, and the harder it is to manage them and to configure them. We need to have a control plane that becomes the source of truth for all the configuration, and so that we can configure those proxies in a dynamic way. And we looked into Kuma. Kuma is a control plane that bundles a data plane already. So if you're looking for a full solution that includes both the data plane and the control plane, Kuma does that. It bundles Envoy, but Kuma per se is a control plane. And Kuma allows you to then make your connections more reliable by adopting a service mesh pattern that would allow you to, by the way, it will allow you to secure, protect, route, observe, and so on and so forth, all of those requests with no effort whatsoever from either you or the teams that are building the apps. Now, the thing about Kuma is that Kuma runs in a portable, platform-agnostic way. So if you have teams running on VMs, virtual machines, Kuma supports that. And if you do have teams running on Kubernetes, as Kevin has demonstrated, we support that as well. So Kuma can support the entire org, and with multi-tenancy, it can support that with a very low operational cost. We are hyper-focused in making sure that the community questions are getting answered. So you can, I'm going to be leaving the meetup open for a few more minutes. If you have any question, you can use the chat in Zoom, or you can ask those questions in our Slack channel that you can find on kuma.io/community.
So Marco, we actually had a question from Vinod. Sorry if I pronounced the name incorrectly. Please feel free to correct me. That he asked, how can we have multiple services on VM or host? And will it be single proxy or multiple proxy in that case?
You would always deploy an instance of the proxy alongside every instance of your services that are being deployed in VMs, which means that, let's say you have 10 different VMs, you will have obviously 10 different instances of your services, one for each VM, and you would have one proxy on each VM as well. So I'm not sure if that's the question and if this is the right answer.
And if you need kind of a sample guide of how to do that, I showed you how to deploy it on Kubernetes. But if you go to the Vagrant directory in the Kuma demo repository, Marco, do you want me to share screen and kind of walk them through that? I can
sure.
do that. There we go. Here we go. So earlier I went through the Kubernetes directory here, but if you go to Vagrant, it kind of walks you through a virtual machine setup. And what you do is, let's say we go to our front-end service. We have Kuma demo data plane service that we deploy alongside it, and all you need to know what could be found here, and you can see how we structured our Vagrant file and the scripts we used to deploy those data planes alongside our services. So does that answer your question? Feel free to, if you want more clarification on that too. And we'll always be on Slack.
Okay, perfect. You can find us on Slack. We're quite responsive. You can open an issue on GitHub. We're quite responsive. We're going to be having, Caitlin, correct me if I'm wrong, we're going to be having one of these online meetups every twice a month, correct? Every 2 weeks?
Yep.
Perfect. So thank you so much for joining this one. Looking forward to see you on the next one. Thank you.